Hello, everyone. Welcome to the first episode of our seminar series called Vision Quantum X. I'm your host, Anuj, and I'm a PhD student at Chalmers University, Sweden. My area of research is experimental quantum computing. I'm always intrigued by the recent advancements in quantum universe, which compelled me to start this channel, where I will be inviting researchers across the globe to share their perspective and discuss their research. Today, in the inaugural episode, I welcome Dr. Jeroen Verjauw. Jeroen studied his PhD at IMEC, Belgium. He successfully defended his PhD in August 2022. I first met Jeroen in my first years of masters back in 2020 when he was my co-supervisor. He helped me to get understand the overall quantum computing and also enabled me to get some hands-on experience with a superconducting quantum computer. Hi, Jeroen. Thank you for joining us today.
Thank you for having me.
So, how would you describe your journey as a PhD scholar?
This has been quite an adventure, especially because in the group I was working in, we essentially started group, or I was actually there from the first day. So I really saw all of the different steps in building a lab, doing the first experiments. So it has been quite a journey, and I think the things we have been able to achieve, me and also the group, they have been quite promising for the future of quantum computing.
It's great to know. So I had the opportunity to go through your research paper. So I will put the link in the video description as well. So personally, I found the paper very, very interesting. So one of the limitations we see is like in superconducting qubits, it's reproducibility and high coherence. But reproducibility is still an issue that many of the researchers are tackling in their own way. What you have done is you have used the CMOS industry compatible fabrication processes, and you have tried to make the qubits more reproducible by leveraging those CMOS tools. So Yaron, now I will give you the platform so where you can discuss your research basically in detail.
Thank you. Okay, so again, thank you, Anuj, to invite me to give a talk on the things I've been working on during the last year of my PhD, where I, and together with the group, have been looking into different ways of fabricating superconducting qubits, more specifically to create a different, or create Josephson junctions in a different way. To look into the large-scale fabrication of these devices if we really want to make a feasible and practical quantum computer. Before going directly into the research, I would like to get everybody on par and to actually discuss a little bit what is necessary for creating a practical quantum computer. So a quantum computer which will effectively enable us to solve very complex problems. For this, I would like to show this nice figure here, where on the x-axis we have time, where we are currently around year 2020, and on the y-axis we have the number of qubits. And in recent years, I think everybody has actually heard about this in the news, is that we have reached a level where with the processor that we currently have, we can effectively, sorry about this. So, okay, we can effectively simulate specific things on quantum hardware faster than we could do them actually on classical hardware. And this is what we effectively call quantum advantage. So we already have been able to do certain simple complex tasks faster on this quantum hardware compared to simulating them on classical computers. However, if we really want to solve complex real-life problems, we would actually need many, many more qubits to get to a threshold that we could create a practical quantum computer. Now, we see that it is estimated that the number of qubits we would need for this would be in the millions. And the reason for this is actually twofold. So we need many more qubits because the idea is that we want to, of course, solve these real-life problems, and essentially to really translate these real-life problems onto quantum hardware. it has been shown that you effectively would need many qubits to do so. That's the first thing. And here I want to notice that even if you would have perfectly working qubits, it would still need many, many of these qubits. And this brings me then to the second point here, is then, of course, because our qubits are, well, let's say real-life qubits, they're not perfect qubits, and there's still some errors associated with them. And for this, to actually cope and to still do meaningful calculations, we need to have a way for correcting for these errors. And again, this will create a certain amount of overhead in the number of qubits that we need. So that's the first part here. So we need more qubits, but we also need better qubits. And that's also where I eventually will try to come in with the research I've been doing. The reason why we need better qubits is essentially to reduce the constraints and the threshold on the number of qubits that we would effectively need on chip to actually let them work with one another to create a quantum processor. So we could actually summarize this as, to scale up, we effectively need many well-behaving qubits. That's the general idea to really make a practical quantum computer work. Now, of course, this is not all that simple. So then the question is, why is it hard to make many well-behaving qubits? And this can be considered from the point of view that if you put more and more qubits on the same chip, you will effectively get more tight constraints on the design parameters. Or differently said, so the more qubits you have on chip, the more important it is that these qubits are behaving and they look exactly the way you want them to, the way you actually designed them. Now, the actual qubit and device parameters, they depend strongly on the way you actually fabricate them, and the way currently state-of-the-art devices are fabricated, that's not adequate to really go to these very large numbers of millions of qubits, because this still has a lot of inherent variation. Now, this is actually something I would like to, or the analogy I would like to use for this is that you have a certain design you put forward for your chip. So for example, if you would be doing 3D modeling, you have a certain expectation of what you actually want to achieve. But if we then actually would fabricate them, so considering that this is a 3D model, I would put it on my 3D printer at home. I do the fabrication. What I would actually get in reality, it would be something like this. And as we can see here, fabrication is inherently imperfect. And this, or at least in the way currently we are creating these state-of-the-art devices. And this is something we have to acknowledge and try to see to cope with this. Furthermore, another thing we have when making these devices is that we have lossy oxides, which are inevitable on top of our devices, and they will reduce their performance. And also in case of qubits, it will limit their lifetimes. So again, here, it's very important to properly consider which fabrication techniques we need and which materials which we will be able to use to create the best performing devices. Again, to really go to this large scale number of qubits. And this brings me then also to the part of the research goal I have been focusing on. So I effectively have been focusing on CMOS fabrication techniques. CMOS fabrication, that's essentially a technology which is used to manufacture all the chips you essentially find in your phones, in your tablets, in your computers, even in your cars. And the importance here is that you can effectively create large-scale high-precision, or that you have large-scale high-precision fabrication, which focuses on reproducibility and low variability. This essentially means that you can make a lot of good copies of the same thing, and they will all work as intended. And that's effectively also one of the strong points that I had here at or when I was working in my group. So effectively, as you can see here, this is a nice picture of the 300 millimeter clean room fab that we that I had at my disposal to try and do experiments on. And here's a nice picture of one of these big wafers used in CMOS manufacturing. So here, Sorry for this issue here. This should not have been there. My apologies. In any case, so the material I have been investigating here is aluminium. It's the preferred Josephson junction material, which is a good barrier oxide. However, the way how it's actually being used, so the state-of-the-art aluminium Josephson junctions, it's not compatible with large-scale CMOS manufacturing. So usually devices are made on small chips, relatively small, of 1 centimeter on 1 centimeter. But that's not feasible on these 300 millimeter wafers. And from that point of view, we effectively need to find new ways of junction fabrication. And this brings me then to the manufacturable aluminum overlap junctions that I have been investigating during the course of my PhD. So again, I want to emphasize here that we're entering an era of large-scale fabrication for state-of-the-art qubits. And these state-of-the-art qubits currently are fabricated with different techniques like shadow evaporation and liftoff. And usually also these devices are fabricated on high resistivity silicon and sapphire substrates. But again, considering these the necessity to go into CMOS manufacturing, these are incompatible with this large-scale manufacturing. And from that point of view, we have been looking into different ways of effectively creating these devices, these Josephson junctions. And a relatively straightforward and compatible way would be an overlap Josephson junction. Now, the idea here is that we have two separate patterning cycles with a vacuum break in between. In order to, in the first patterning cycle, we would do a bottom electrodes and also the large structures which you find on chip. I'm thinking here of the capacitor pads of your device, of your qubit, but also the ground plane and the resonators that you're fabricating to send signals to your device and also do readouts. And then in the second patterning cycle, you effectively make the connection to create your effective Josephson junction. Now, as I said already, you have a mandatory vacuum break in between, and this is problematic because this introduces uncontrolled oxidation. So essentially, you will have native oxides where you would like to create a good working junction. So for this, we need to apply an Argon milling between these two patterning cycles because it's necessary and critical to first remove this native oxide and then do a proper clean oxidation to create a good junction barrier. So an important reason why going for these overlap type of Josephson junctions is that it has been shown in recent years that they can really already create good performance with maximum relaxation times going up to 80 microseconds. These were the best values that we were able to find, so there was already something very promising there. However, it was shown that it was not fully compatible with CMOS fabrication. And that was actually one of the first things I wanted to go and investigate, was that even though we already see very interesting and promising results from previous studies, I wanted to see if we could really make something that was large scale compatible. So really something we could push into the large clean room to get potentially even better devices. That's then also, that ties in a little bit with the next point, that I really wanted to see what the highest performance of these devices actually could be that was fully large scale compatible. And associated with this is, of course, what the actual limiting losses were. More specifically, I wanted to investigate if this was associated with the Argon milling, because as I said before, this Argon milling is a crucial and necessary step to perform. So I wanted to see if this was already device limiting when creating our qubits or not. And that's important if we then further want to improve devices and fabrication in the long run. Now, in order to do this, I did two types of characterization. So first and foremost, I looked into electrical characterization combined with electromagnetic simulations. That's one part. And then in a second part, I went into interface characterization to really get a better understanding of the morphology of the different interfaces of our fabricated devices. So for the electrical characterization, first,
so Jeroen, can I sorry to
yes,
disturb you. So can I ask you a question here? So you have shown like so you are investigating on overlap junctions. So you also stated like a lot of research groups are still using a shadow evaporation or other techniques. So do you see any drawbacks of overlap junctions? Why other groups are not maybe investing that much in overlap junctions? Is there any clear drawback, or it's just people are keep using from few years, that's why they are not trying this now, and some research groups are starting to investigate now? Is this?
So the main reason why going into or why people are using the Dolan bridge, so the shadow evaporation junctions, is because they create the most pristine type of junctions. Essentially, they create the best type of barrier oxides. And also when considering, or if you then would compare it also to the overlap junctions that we have been investigating, is this extra step of argon milling is actually rather invasive on the performance as well, because this argon, it has been shown that heavy argon milling or argon milling in general can deteriorate the performance of your devices. So that's the reason why it is on relatively small scale to go for this shadow evaporation junctions, because the type of junction that you actually create is more pristine.
So historically, I thought like these overlap junctions are easier to fabricate. So hasn't I don't know, 20 years before someone has already tried it or not? Did you see in literature?
I think you mean that if people already tried the overlap junctions before.
Yes. Because I think someone would have tried maybe even shadow evaporation, because this is easier to do, and shadow evaporation and other have different sophisticated things that people are now comfortable with. But I think overlap itself is a very
straightforward procedure.
Very straightforward.
Yes, that is true. And people have been trying to do this type of overlap junctions already a long time ago, but at that stage, it was considered that essentially the quality of your junctions was not good enough to make proper qubits, and because of this, people have been focusing mainly on the Dolan bridge. Before then, now coming back to it and seeing that the performance can actually still be on par with things you can find in state of the art.
Okay, so did there some process change that enable now, or tools basically that are helping you to do things even more pristine form?
It is an idea. The idea there is that by tweaking and optimizing your fabrication of your of the way you're creating your overlap junctions can effectively improve your devices, and as I said, up to or on par with what we find in other state-of-the-art implementations which do use shadow evaporation junctions.
Okay, perfect.
Yeah, good. So then what we did here, or the first type of characterization was just looking at coherence times and randomized benchmarking. Our type of qubits, because I already showed it on the previous slide, we did different types of qubits, but the best device we were able to get the best results from were transmon qubits, so a double pad transmon qubits. And the relaxation times and coherence times we were able to extract were approximately, or mean values of about 60 microseconds. So already a relatively high there. I've even been able to measure values up to 100 microseconds on specific devices, as I can show you here. So this has been the general characterization of coherence times of our devices. But aside from that, I've also investigated these devices by doing randomized benchmarking. And what we saw here was that the average single gate fidelity was already going or was already surpassing thresholds of certain error correction codes. So this again gave us confidence that the type of devices that we were fabricating are effectively viable if you want to consider to do something more complex with them in the future. Then next, I wanted to investigate the effects of etching and substrates, because again, we need to consider that the way we are fabricating our devices in the lab, that's not going to be fully transferable to what we have in the fab. So these two are different. And from that point of view, I wanted to explore the performance of large-scale compatible processes and substrates, where we can consider, if we look here at the graph on the left one, we have, if I quickly go to the next one. So essentially what I've been gathering here are T1 statistics, where I'm considering different type of bottom electrode etches and also different type of substrate resistivities. Here on the left, we consider to have the type of fabrication that is most akin to what we would find in state of the art, while on the right we find devices which are closest or more closely related to what we would find in the clean room. So in the big CMOS compatible fabrication facility here. So, and an important observation is that there doesn't seem to be a significant difference between wet and dry etch processes and 3 versus 20 kilo centimeter wafers. So again, here, these were devices fabricated on the most compatible or most closely to the state-of-the-art fabrication. And again, we did see this type of T1, so this relaxation time, which would go up to this 100 microseconds. And this gives us confidence that the qubit lifetimes are not compromised by this dry etching manufacturable process on this 3K wafer substrates, which are also found in the big fab facilities we have here at our disposal. And then in a next set, so in the next set of experiments, I wanted to investigate where then the losses of our devices were actually starting to limit the performance. For this, I have extracted the quality factors of different qubits or different qubit types, as we can see here. So we have a double transmon or a double pad transmon and 2 exmon type qubits with different gap sizes. And based on this, we did some simulations and then plotted these inverse quality factors of losses versus the participation ratios. And what we found here was that, you look here, this nice linear fit, we did see that these losses, they are scaling linearly with these capacitor pad participation ratios. Here, an important thing I want to point out before going to the next point of interest is that effectively, for this fit, we only used the data given by the 3 qubit types that we have been measuring. Now, this is important for the following reason, namely on chip, aside from these 3 qubits, we also had a high quality factor or high Q resonators. And what did we find? We found that these resonators are effectively on the same linear fit. So this linear fit is actually agreeing with the resonators that we were measuring on chip. This essentially shows us that both these qubits and these resonators, they effectively have the same type of device limiting losses. And since you can consider these resonators to be essentially qubits without a junction, it could be inferred that, again, these qubits here, they are limited by losses found on the surfaces, so on the capacitor pads or on the silicon substrate, essentially. So again, this very nicely shows us that the way we are fabricating our junctions with the overlap junction approach is effectively not limiting our devices that we have been fabricating. Now, ideally, we want to get rid of these losses, of course. So we want to still push these qubits to higher and higher, let's say, coherence times and relaxation times to really create the best qubits possible. But once we will be able to get rid of these participation ratios as much as possible, we will start to run into different problems. Now, if we were able to get rid of these participation ratio losses or capacitor pad losses, we would get a residual loss, which would correspond for a T1 time of approximately 131 microseconds for a device around 3 gigahertz. And at that stage, we are considering to be limited by different types of losses. And the things we have been thinking about have been listing here. So we are considering quasi-particle tunneling, stray junction, and also Josephson junction, more specifically surfaces in the vicinity of the junction, but also the junction barrier itself could be a place where we actually have losses. So these will be things which will be further investigated once we will be able to push these device limiting losses even further down and trying to get more, let's say, that we actually can start seeing these residual losses pop up more and more. And to this effect, I have already been investigating the devices with the highest Q factor, so the lowest losses, and effectively I have already been able to find some interesting, or I already have some conclusions on this, is that I already have been able to see the quasi-particle losses. Because for this, what I did find was that in certain of the T1 traces or relaxation time traces, I did see a quasi-particle signature with a double exponential decay, showing us that we already are getting sensitive to one of these residual losses. However, at this stage, it cannot be determined, or quantitatively, it cannot be determined how much to this T1 limits these quasi-particles are currently contributing, and new experiments will be needed to conduct to get or to be, let's say, to really distinguish between these residual losses. New experiments will need to conduct that we can get more, or that we would get prone to one specific of these type of residual losses to really see where the next challenge will lie. Good.
Jeroen, can we go to 2 slides before, where you show the slope, where you have shown the
Yes.
This slide, so you have shown so the resonator has like also a bit of, I'd say, more standard deviation, like in terms of losses.
Mm-hmm.
Also, when you say, means I'm just curious, like you talked about the surface participation, have you tried like making the resonators with different gaps and seeing if they follow the same principle of same linearity curve?
Yeah, so for the resonators themselves, we have not considered to do different gaps at this stage.
Okay.
It has just been one specific design that we have implemented on all of the different chips, but we didn't go into different gaps at this stage.
Okay, but ideally they would still follow, I think, the same line. That's what you expect,
That's
right?
the idea, yes. The idea is that indeed, if you would get bigger gaps, you would effectively you would follow this trend all the way down until you get to the same things with what you would get, sorry, for the qubits.
Okay, perfect.
Good, and then as a final part, we want to then look into the device itself to really do a proper morphology and interface characterization to really see what's happening within our junction and our device. So again, One of the important things in this study was to look into the effects of creating this alternative Josephson junction, this overlap junction. And of course, the most important part is the Josephson junction itself. So from that point of view, we did an interface characterization of the junction as shown here. And to look at the effects of the argon milling, we did see that here, looking at the picture here on the left, that there was no structural defects, or that there are no structural defects present when looking into the junction here. We did see, however, that there are argon and silicon traces present. If we look here on the far right, the EDS images here. So again, we did see contamination of about less than 4% within our junction. So it's important to acknowledge that there is contamination within the junction. But from the previous results, so from the electric characterization, it does seem that they are only part of residual losses at this stage. Again, it's important to see that they're there, but at this point, they are not limiting our device performance. And then the next interface that I would like to highlight here is, of course, what I was discussing before. This was where the actual device limiting losses are located, and this would be at the bottom electrode. So essentially found on the capacitor pad of our qubits, and also at the large structures. And there we find, again, these device limiting losses, which are considered to come from native oxides at the metal air and substrate air interfaces, as we could see here from the EDS in the center. And also from, this is also something we could see here from the silicon traces, we do seem to have also sidewall residues, and these are considered to come from fabrication specific techniques, which are also there. So it's not sure how much they would actually contribute to the device limiting losses, but it is something which has to be taken into account when trying to further improve the device performance when trying to do post-processing to get rid of these both these native oxides and the sidewall residues. And this would bring me to the conclusion. So within the study for these manufacturable overlap junctions, I've been able to show that there is a process which is fully compatible with CMOS fabrication, which is a good news because it means that the this fabrication technique that we have well studied and developed to a certain point can now be transferred into a fab environment to see what is actually then feasible if we use fabrication with specific tools that has much more, let's say, controllability. How this will affect device performance, how it will affect variability, and also reproducibility on a large scale. We have also seen here that the junctions, they are not limiting our relaxation times up to 100 microseconds, but again, because again, we effectively have measured these values. And we also saw that it's not argon milling that is limiting our devices at this stage, but it is the capacitor surface loss that is limiting our T1. And with this, I would like to thank you for your attention. And if you still have questions, please go ahead.
Yeah, I will also put Jeroen's email ID in the description. So thank you, Jeroen, for like the very interesting research talk. Like I really appreciate it. I have some questions. Means I was reading through paper, so I have a few more questions as well as from the slides you have shown. So one of the things I've noticed in your paper, you mentioned you have around the standard deviation of resistance is around between 2 to 5%. And I was expecting, like, since it's a standard CMOS process with etching, means the deviation should be less. And let's say even if it's this stage of 2.5%, first question is why this is 2 to 5, and second question would be then how to reduce this, because this is also an, say, active research to make it more reproducible.
Yes, so from that point of view, that's a good point. And here I want to emphasize that the results that I have been showing here is only a fab compatible process, which has been conducted within a lab environment. So from that point of view, if you really want to consider the reduction in variability and to see the effects, you have to go to real large-scale fabrication, which at this stage has not been done for these devices. So that's these have been essentially fabricated on coupons, so relatively small number of devices have been fabricated, though because we have been able to show that it is fab compatible, the next step, and that's also what's currently happening within the group, is that we have been transferring this to the fab environment. And there we would then do large-scale characterization of junctions, enabling us to see how the variability and reproducibility will actually change.
Do you have any expected number, like how much variation you will expect from the CMOS?
I think this also still very much depends on how far you are in the optimization process when running your lots through your P-line.
Okay. One thing, like, okay, I just want to ask is, so we have talked about you are limited by the metal layers participation. So when we talk about metal air, so are we talking about the native oxide that forms, or why the metal layer losses are important?
It is the native metal oxides that would grow after essentially after or even during fabricating your device.
Yes.
You essentially will, well, native oxide is unavoidable, right? So from that point of view, if you want to get rid of this, you need to consider two things. So essentially the losses, they depend on the inherent losses of your interface layers and also of your participation ratio. Participation ratio being, it's a measure on how strongly the losses within your oxide can actually couple to your device and actually can deteriorate the performance of your device. Right. So from that point of view, there are two options. So either you try to improve your participation ratio, or let's say reduce your participation ratio. This can be done in a couple of ways. What people generally have been doing over the last 10, 20 years is making your structures bigger and bigger and bigger, that you're effectively diluting your electric fields, that it's that any inherent loss in these interfaces is actually reduced. That's one option. But of course, you can't keep on doing this indefinitely, because you would end up with structures which are starting to get even millimeter size and much larger. And that's something which is, well, something you don't want to do if you want to scale up to very, very large number of devices. So another option to reduce your participation ratio is, well, there are a few options there as well. You can either go deeper into your substrates, trying to reduce the participation ratio associated with the substrate air interface, because that's also an important interface considering losses. Another important thing to consider is you don't want to have any sharp edges, because sharp edges would mean that you're concentrating electric fields. So again, from that point of view, that's also something which you might want to consider when you want to try to reduce your participation ratios. So that's one part. Of course, again, as I said, the inherent lossiness of your interfaces is also important. And from that point of view, you can do something else. You can actually try to get rid of these inherent losses. And from that point of view, and that's also something I discuss in the paper there, is that you can consider to do some post-processing techniques to try and get rid of these native oxides, both from the metal air and the substrate air. And afterwards, it might be there might be a way and that's also some speculation there, is try to prevent reoxidation of these lossy interfaces by capping them with some type of material.
Yeah.
Now,
Yeah.
again, this is speculation, but these are different ways that people also and we in the group have been thinking to see if there might be some possibilities to try and still improve the device performance. But again, highly speculative at this point.
Yeah, I was also thinking on the lines of capping with some other material so that it would be, I think, maybe more like less lossy, basically.
The issue there is from the moment you introduce again an interface, it might again become more lossy. So it is a very delicate interplay to see what you actually want to achieve. It's not straightforward.
Yes. Also, like in one of their slides, you have shown like, okay, you have the problems with argon argon kind of implantation. You have like, you have shown that you have on top electrode when you have studied, like you have some traces of argon buried in. So I think we can go back to the slide. I think one before this.
This one.
Yes. So is this is this have to do with some force that you use with the argon milling? Can you reduce the force to maybe have a lesser implantation?
Yeah, so this is already within the scope of the tool that we have been using. This has been already an optimum of, as you correctly point out, trying to, or just reducing the power as much as possible while still sufficiently cleaning the native oxide from the bottom electrode. So this already has been an optimized setting, again, within the tool that we have been using here. Again, if we then would go to a different type of tool in the fab, this would effectively mean that this recalibration needs to be, or this calibration has to be redone.
And maybe the industry tools that in CMOS would have better control and so more parameters to.
I do fear that you would always have some remnants of argon inside of your device. Again, how detrimental they will be at this point, I don't think it's going to be the main issue or the main point of concern.
Okay. So I don't have more questions now. I think you have answered everything. And also I encourage all viewers to go through your paper. Like that has a lot of more details. Even the supplementary is really important to see if someone is like in fabrication and want to try this method. I think all the like always good things can be found in supplementary information as well. So by this, I would end this meeting, and I will thank again Jeroen to like give us this really nice talk. We get to see more of what is going in the fabrication and to make the things reproducible and to make a quantum computer a reality, because you need to have more and more qubits, and this is a bottleneck which we have to clear as a community. So thank you, Jeroen.
And thank you for having me. It was a pleasure to talk about the research that I've been doing.